So now we're going to look at some examples of the assembly language that is used to specify the operation of the data path we just designed, and what they look like in machine code as well. So when you write assembly language, you're going to write a line of code like this. The assembler will translate that into a 32-bit machine code instruction that looks like this. That's going to be in the instruction memory, and it's going to be loaded by the address from the program counter, and it's going to specify what each individual component of the hardware will do. So we're going to look through a few of these examples and see what they look like. So the first example we're going to look at is what we call R-type instructions in MIPS. These machine code instructions use registers to specify the data that they want to operate on, and typically use the ALU to calculate a result. So these have an opcode, which is 6 bits, and then 3 registers specified by 5 bits each, and then a shift amount, which we're going to not use right now, but will become handy later, and then a function code, which extends the opcode. So normally, the opcode tells the machine what to do. With R-type instructions, especially ALU format R-type instructions, the opcode is going to be all zeros, and then that's going to tell the machine, I want an R-type ALU instruction, and then it looks at the function code to decide what actually to do. In this case, add is 1, 0, 0, 0, 0, 0, and subtract is 1, 0, 0, 0, 1, 0. And we can see what all of those codes are on the sheet, right? Make sure that you download, print out, and reference this sheet, and it tells us, for example, that add is 1, 0, 0, 0, 0, 0, and the subtract is 1, 0, 0, 0, 1, 0. And there's a bunch of other stuff there as well that we'll get to. So we're just looking at the R-type instructions now as the first example. We call these register format instructions, and there are 3 registers that we use. RS and RT are our source registers, and RD is the destination register. And if we look at the hardware for this machine and remind ourselves of what we're actually doing, RS and RT come from the instruction and are presented to the register file, which then looks up the value that's in RS and RT and presents those to the ALU. We have to make some choices based on these multiplexers, but generally that's what happens. And then the result from the ALU comes back, passes through a multiplexer, and is presented at the register file to input D, which is specified by RD. And so again, we have to make a few choices in our multiplexers, but in general, that's what happens. So we specify RS, RT, RD. Those 2 values are presented to the ALU. The ALU does something based on the function code, and the result is placed back in the register file in the register specified by RD. And so, in fact, we can look at this here as well. So this is, again, the same machine I just showed you. A few little differences, but in general, the same machine. And we're going to show you what happens when we do add into T8 the value that's specified by S2 and S1. So it's going to take S1 and S2, add them together, and put the result into T8. So let's watch what happens. First of all, the program counter addresses the instruction memory and gets an instruction. This is always the first step of every instruction, because before we have the opcode, we don't know what the instruction is. We don't know if it's an add instruction or something else. And so the first step is always going to be to decode and look at the opcode and say what happens. Once we've done that, then we can specify RS, RT, and RD. The opcode will tell the control that RD should be 1, and so that value passes through here and looks up the place to put the result. Then the register file looks up the values for RS and RT. This multiplexer chooses 0 to pass the register result to the ALU. And then the ALU result is passed back through here, presented again. This multiplexer chooses 0, so it goes through here, and the result is stored in the address specified by RD. And all of that control happens based on the opcode being R-type, which is 00000, and the function code being add, which we already showed you. Those values, the opcode and the function code, go into the control logic, which we'll design later, and then out come the decisions for each of these individual components. What the ALU does, what the memory does, which it's not doing anything right now, what these individual multiplexers do, and a bunch of other stuff. And so your goal is to understand just what the R-type instructions do, what's available in terms of R-type instructions, and what the hardware does to implement each of these individual instructions. So that's R-type instructions. And now we'll look at I-type instructions as well. I-type instructions are for literal value. This means that instead of storing information in a register, we have the information available right in the instruction itself. And you can see it right here. This is the format for the instruction. We have an opcode that tells us which instruction we're doing, opcode. And then we have a couple of registers, and we'll talk about how we can do this with only 2 registers. And then the rest of the instruction is a number, a value that we present directly to the ALU. Okay? So this number is anywhere between 1 and 2 to the power of 16, which is 64,000, or if it's signed, it's between negative 32 and positive 32,000, about. And we call this an immediate value because it's available immediately in the register itself. Available immediately in the instruction itself. We don't have to look it up in a register. We don't have to look it up in the memory. It's right there in the instruction itself, stored in the instruction memory. And so what happens is we're going to take RS, and we're going to take the immediate operand, and we're going to combine them, present them to the ALU, and the result is going to be placed back in RT. Now this is one of the little, I wouldn't say problem, but a little quirk of MIPS is that in some instructions, RD is the destination register in the register file, and in other instructions like this, RT is the destination register in the register file. If you watch the other set of videos on the design of the data path, you can see why. The MIPS machine has been evolved over a number of years, and this is sort of a little compromise between making instructions too large, between making instructions too complex, but it does mean that we have to decide here whether the destination register is going to be specified by RD or RT, and that's what this multiplexer does. The 31 we'll talk about later on. So we can choose RT or RD for the destination register. In both cases, the result comes from this multiplexer, which can take its result from either the ALU or the data memory or the next address logic. And again, we'll talk through those as we go. But for now, all we want to do is provide an opportunity to take a value straight from the instruction rather than having to look it up in memory. There's a lot of good reasons to do this. We want to just add 1 instead of add some value that's in some register. It's pretty useful. So there's no function code here because the space normally taken up by the function code instead is taken up by the immediate value. So the opcode has to specify entirely the function. The assembly code language is often specified by add I sub I, right? The I format instructions, and again, you can look it up in your sheet. Each I format instruction has an I here, and you can see add immediate unsigned, and immediate, or immediate, XOR immediate, set less than immediate, and then you will see later on the load and store instructions are also immediate format, but we'll talk about those later on. So the immediate format instructions take the value from the immediate field in the instruction rather than a register. RT is now the destination. We talked about that already. And so this is why we need that multiplexer. The problem with immediate values is that they're 16 bits, and the ALU and the rest of the machine is 32 bits. So we need to take that immediate value and extend it to be a 32-bit number so the ALU can properly add it or subtract it or whatever to the other register value that was looked up from the register file. And the way that we do that is sign extension. You can look back in your 2's complement notes to look at what sign extension is. But basically, we need a little box that sign extends the 16-bit immediate value into 32 bits. And then we also are going to completely bypass the register file. And so that's what this instruction is. This is now the I-type instruction. This is add I into T8, the value that's in S2 plus 61, some random value. So this is adding a constant or adding a literal value, or we call it in assembly language an immediate value. So it looks like this. First, again, we address the program counter to the instruction memory and grab the value. This time, however, the immediate value is sign extended, and then the multiplexer at the ALU input chooses 1 instead of 0. So we choose the sign extended immediate value instead of RT. RT is still there, right? Some value is looked up from the register file. We just don't use it. And then RS is presented here as usual. That's the only thing that can happen here. RS is always presented to the register file and looked up and presented to the ALU. And then here, we're going to choose with this multiplexer to treat RT as the address of the destination register rather than RD, because the space that was taken up by RD is now the immediate value. And we can see that in the format here. If you look at these 3 different formats, these 32 bits have to work always the same way. The opcode always has to be the first 6 bits, because until we know what the opcode is, we don't know what to do with the instruction. Then RS and RT are always the same, but in the bottom half of the instruction, R-type instructions can specify RD, but that same slot is taken up by the immediate value, and so RT has to be the destination register. So RT is the destination register, and we use that multiplexer. And then the ALU calculates its result. Again, through this multiplexer choosing RS equals 0, the result is placed back to the register file, but now it's addressed by RT instead of RD. And that's the final result. And in the next video, we'll talk about load and store instructions.